Hey everyone, welcome to The Explainer. Today we're diving into Lecture 40 from Skip Uni, and we're totally demystifying vectors in C++. If you've been wondering exactly how to use vectors in C++, you're absolutely in the right spot. Think of this as your go-to STL vector tutorial. We're going to break down exactly how they function as dynamic arrays in C++, and we'll also master the most essential vector functions in C++. But before we get to the good stuff, we kind of have to talk about the headache that is standard arrays. You know the deal, they're incredibly rigid, they have a fixed static size, meaning you have to know exactly how much data you're dealing with right out of the gate. And honestly, that just leaves you with zero flexibility when your program is actually running.
So here is our roadmap for the explainer today. We're kicking things off with the dynamic array solution. Then we'll look at syntax and memory allocation, clarify the whole size versus capacity thing, dive into the dynamic resizing twist, and finally wrap it all up with powerful built-in functions.
All right, Section 1, the dynamic array solution. Let's talk about overcoming those static arrays.
So standard arrays presents this massive problem, right? They are just way too rigid, stuck at a fixed size. If you want to make them dynamic manually, well, you're suddenly forced to micromanage your computer's memory using the new and delete keywords. It's tedious, and let's be real, it's super prone to errors. But this is exactly where STL vectors step in to save the day. Because they're predefined inside the standard template library, vectors just automatically grow and shrink as you add or remove your items. They handle all that messy memory management for you, dynamically behind the scenes. You literally just include the vector header file and you're good to go. No manual allocation headaches required.
Okay, moving right along to Section 2, syntax and memory allocation. Let's look under the hood.
The syntax for setting this up is beautifully simple. You just type the keyword vector, throw your data type into some angle brackets, so int for integers here, and then give your vector a name, like v1. That one single line of code creates a vector that strictly holds integer data. But here's the really cool part. Under the hood, just like standard arrays, a vector stores all this homogeneous data right next to each other in contiguous memory locations. Why does that matter? Because it means you can randomly access any element instantly. We're talking O1 time complexity. It's totally dynamic, but still incredibly fast. Now, here is a crucial behind-the-scenes detail, and definitely keep this in your back pocket for coding interviews. Where does all this physically live inside the computer? Well, when you declare v1, that vector object itself is created on the stack memory. The stack is, it's limited, it's fast, highly structured. But the actual elements you start pushing into it, like the numbers 10, 20, 30, they don't go on the stack. They're actually stored dynamically out in the vast, flexible heap memory. And utilizing that massive heap space is the exact trick that lets your vector expand or shrink at runtime without, completely crashing your program.
Next up, Section 3, size versus capacity. This is all about understanding our limits. To really wrap your head around this, because it's a super important distinction, imagine a giant drum. Now, if this drum is filled exactly halfway with water, the actual amount of water currently sitting inside, that represents the vector's size. It tells you exactly how many elements you actually have right now. But the total volume that drum can physically hold, all the way up to the very brim, that is the capacity. So capacity tells you the absolute maximum number of elements the vector can hold before it completely runs out of space. So if we initialize a brand new vector with exactly 3 elements, its size sits at a value of 3. But crucially, its capacity is also exactly 3. At this exact moment, our drum is totally full. Size and capacity are a perfect match. Which brings us to Section 4, the dynamic resizing twist. Let's see how these things actually grow. So what actually happens when the drum is full, but we absolutely have to force more water in? Let's say our vector is maxed out, 3 out of 3 slots taken, and we use a command like push_back 40 to jam a 4th element into this full structure. Does the system just kind of squeeze it in there? Nope, absolutely not. The vector internally provisions a brand new structure over in the heap memory, and it does it with double the original capacity. So it jumps right from 3 to 6. It then seamlessly copies your original 3 elements over to this new space, drops in your new number 40, and just leaves the remaining 2 slots completely empty.
Let's look at the numbers here. Before we push that new element, size and capacity were perfectly matched at 3, right? But after we run that pushback command, our size bumps up to 4 because we have 4 numbers now, but our capacity, that has completely doubled to 6. You've got your 4 elements plus 2 empty slots just waiting patiently for whatever you add next. The vector basically went out and bought a bigger house so it'd have room to grow. And here is what's truly mind-blowing about this whole architecture. This doubling trick, it doesn't just happen once. It repeats infinitely. If you eventually fill up all 6 of those slots and you try to add a 7th element, the capacity doesn't just bump up to 7. It instantly doubles again, straight to 12, then 12 to 24, 24 to 48, and so on. This is exactly how vectors pull off their dynamic scaling in the heap memory. And they do it all without you having to manually write a single line of memory allocation code. It's brilliant.
Finally, Section 5, Powerful Built-in Functions. Let's look at this rich STL library. Vectors are considered such a user-friendly tool because of this incredible toolkit of ready-made STL functions. Let's just quick-fire through 8 essential ones. First up, pushback, which we just saw in action. It just adds a new element to the very end of your vector. Next is popback, which does the exact opposite. It removes the very last element. Then we've got size to tell us our current element count, and capacity to show us our maximum limit. If you need to wipe the slate clean, clear instantly deletes everything inside. Want to just take a peek at your data? Front gives you your very first element, while back grabs the last one. And finally, empty is this really handy quick check that returns true if your vector has absolutely nothing in it, and false if it contains data. It's just a phenomenally complete tool set that makes your programming life so much easier.
So we have covered a massive amount of ground today, right? From the really rigid limitations of standard arrays to the completely magical expanding capacity of C++ vectors. But as we wrap up this explainer, I want to leave you with a bit of a provocative thought. Given that doubling a vector's capacity requires physically copying all of your existing elements over to a brand new memory block in the heap, what do you think are the hidden performance trade-offs of using vectors in really demanding, highly memory-intensive applications? Like, does that automatic copying come at a hidden cost to your algorithm's time complexity? It's definitely something every great programmer needs to wrestle with as they optimize their code. Think about it. Anyway, thank you so much for learning with me today, and keep exploring.